Previous video we talked about oxidation and reduction in organic chemistry, and that's very relevant to our discussion of alcohols as a functional group. The first instance of that is going to be as we start to think about different reactions that are used to synthesize alcohols. How are we going to make this functional group from something else? And one set of reactions that can be used to synthesize alcohols is our set of reduction reactions. And specifically in this video, we're going to look at how you can reduce aldehydes and ketones in order to generate alcohols. Now, let's remind ourselves what we mean by reduction. Right? We said if we turn, let's get a pen here, a carbon-hydrogen bond to a carbon-oxygen bond, that was oxidation. And so it makes sense that if we go backwards, turn a carbon-oxygen bond to a carbon-hydrogen bond, those are reduction reactions. So the more carbon-hydrogen bonds we have, the more reduced we are. The more carbon-oxygen bonds we have, the more oxidized we are. And again, remember, we're thinking about electron density around the carbon chain. You can imagine hydrogens might push electron density onto the carbons, reducing it. Oxygens and other electronegative atoms would remove electron density from the carbon, oxidizing it. Now, let's look at a general reaction of how we can use these reduction reactions to make alcohols. Well, in the last video we had sort of a spectrum of functional groups that went from least oxidized to most oxidized. So if we're going to reduce something to make an alcohol product, that reactant, had better be more oxidized than an alcohol. And so we're going to take things like aldehydes and ketones, and later in the next video you'll see some carboxylic acids and esters being reduced to form alcohols. So in the arrow here we've got looks like an H in brackets, and that's a hydride reagent. Okay, so this we're going to say is a source of hydride. That's not very neat. Now, what is a hydride? Well, a hydride, let's move here. That isn't working. Where's my pen? A hydride is an ion, and it is a hydrogen that has gained an extra electron. This is the hydride ion. And we really have two sources that we're going to think about for hydrides in organic chemistry. One is our sodium borohydride. It's a very useful reagent. It's not terribly reactive, but it's usually reactive enough. And then the very reactive lithium aluminum hydride. Sometimes it's too reactive, and we'll see the use of these in these reduction reactions. Right now, we can think of both of these reagents as sources of our hydride ion. Okay. So how is the hydride going to be able to synthesize alcohols from aldehydes and ketones? Well, let's show an example of this. Let's take a simple ketone, in this case acetone, and we'll treat it with a hydride source, either lithium aluminum hydride or sodium borohydride. And we can just try to work out in our heads how this is going to react. Well, in order to figure out how two molecules react together, usually the first step in organic chemistry is to identify nucleophiles and electrophiles. And in this case, the nucleophile is pretty apparent. We've got a negatively charged nucleophile right here, a Lewis base. This is obviously a nucleophile. So what is going to be electrophilic in this molecule? Well, we've got this carbon-oxygen double bond, and one of the hallmark things of organic chemistry is whenever you see a carbonyl group like this, you need to think in your head that electronegative oxygen is going to be pulling electron density away from the carbon. And that makes that carbon have a partial positive charge, and it's very attractive to nucleophiles. We're going to see this type of reaction really throughout the rest of the semester. Nucleophiles love to attack carbonyls or things like carbonyls. We see it all the time in organic. We see it all the time in biochemistry. And that's the reaction we're going to use in order to generate our alcohols from this ketone. Okay, so if this carbon is partially positively charged, you might draw your first arrow with the nucleophile attacking that carbon, a new bond forming between the carbon and the hydrogen. Now there's a problem. We have now 5 bonds on this carbon, so we're going to have to resolve it by breaking that double bond and having these electrons go up to the oxygen to generate an intermediate. Generated a new carbon-hydrogen bond. That's a reduction, right, because we're generating more carbon hydrogens. We have less carbon-oxygen bonds. And since this oxygen is now not sharing a pair of electrons, it's negatively charged. Okay. This is usually seen as an intermediate in an overall reaction, and we can protonate that in a second step by the addition of acid to form our final alcohol. In this case, 2-propanol. So we can take some molecule like an aldehyde or a ketone that's relatively oxidized. We can add our hydride reagent as a reducing agent to reduce that carbonyl group to an alcohol group. And that's one way to synthesize alcohols. The next video we're going to talk about how to do this with carboxylic acids and esters, and it's going to be a similar mechanism, but we're going to add a little twist to it.